Hi, I'm Pascal from the Software Composition Group at the University of Bern in Switzerland. I'm in the last year of my PhD and I'm working in the domain of mobile application security. In particular, I investigate vulnerabilities caused by security smells and the corresponding remediation strategies. Now let's start with the presentation. In the next few minutes, I will talk about security header fields in HTTP clients, where we investigate the support of security-related HTTP header fields in the web communication of mobile apps. This work was a collaboration between another member of our group, namely Oscar Niestras, and the University of Auckland in New Zealand, namely Mohammad Ghaffari. Here's a quick overview about this presentation. We first introduce the topic and explain the terms HTTP client and HTTP security header field. Then we present common server-side issues that we have found before we switch to the client-side issues. Finally, we propose two new measures to improve the security of web communication. Let's first talk about the nature of HTTP clients. In specification documents, an HTTP client is usually referred to as a user agent. According to the World Wide Web Consortium, W3C, a user agent is any software that retrieves, renders, and facilitates end-user interaction with web content. So what is now an HTTP client, respectively a user agent? Well, there are three very popular classes of them. Web browsers, which access websites, email readers, which access websites embedded into emails, and mobile apps, which access websites and web APIs to offload data processing. In this work, we focus on the use of HTTP headers in mobile apps. Here, I would like to add a short clarification. Traditional desktop applications can include HTTP clients as well, but they are typically less connected than their mobile counterparts. That is the reason why we will explicitly focus on mobile apps. For those of you who are not that familiar with HTTP headers, here's a quick refresher to keep you in the loop for the next few slides. An HTTP header is used to set up and maintain HTTP connections and consists of several key value pairs, the so-called header fields. There exist request and response headers. However, in this work, we solely focus on response headers that originate from servers. Moreover, there exist several request methods, but we only use the HTTP GET method to trigger response headers. So, what are typical properties of a response header? For example, a header can tell the client whether the request was successfully processed with the HTTP status code that you can see in the first line. Or it can tell the date when the message was originated with the date header field. Or just on what software the server is running. In this work, we focus on response headers that relate to security. But what are examples of such headers? In this response from the Web API server, which hosts api.weather.gov, we can see three header fields that are security related. The server header field reveals the current release of the Nginx web server. In fact, based on this information, we can expect that the server runs a release from May of this year, which is only one version behind the latest stable version available on the Nginx website. Then we have the access control allow origin header field, which indicates whether the response can be shared with requesting code from the given origin. In this case, scripts from any origin can access the resource, which is only allowed when no credentials are required. Finally, there is a strict transport security header field, which forces clients to access a website only through secure communication channels, such as HTTPS. The provided values ensure that the policy remains for 1 year for all subdomains and that the policy can be preloaded. With this knowledge, we are now ready to collect the response headers from app servers, which are accessed by mobile apps. We started to collect connection data of the URLs, which were used in 431 open source apps from the F-Droid market and in 889 random closed source apps from Google's Play Store. From these apps, we could gather more than 9,700 URLs that we further exercised. That is, we sent an HTTP GET request for each URL and we collected the returned HTTP header information. The response from these unique URLs contained more than 65,000 header field values, which we could assign to 439 unique header fields. Interestingly, it seems that many server operators are using custom HTTP header fields to provide some functionality, as we have seen 32% of them only once. Because we did not have the resources to cover every single header field, we focused on the top 50 used header fields. The observed top 50 header fields served 8 different purposes. As you can see, the most prevalent purpose was performance optimization, followed by advertisement and security. Cookie management, content redirection, and privacy were not used much. In this work, we only focus on the security-related header fields. We consider a header field security-related whenever it has an impact on security. And therefore, we also consider header fields in the advertisement category that leak data, although that may seem inappropriate without any context. In the end, we could identify 16 header fields that relate to security, which are shown in this slide. However, some of them appeared more frequently than others. For example, we could attribute a whopping 15% of the reported header field values to the advertisement category. The advertisement category only consists of these 4 header fields, which were primarily responsible for leaking version information in their received responses. Previously, we discussed the server-side use of such headers. But what is the value of server-side security when there is no support available in the used client-side HTTP applications and libraries? Let's switch sides and continue with the investigation of client-side applications and libraries. First, we take a quick look at modern web browsers, which are generally considered to be secure in terms of web communication. Here you can see the relative support of security-related header fields in popular web browsers. You can see that almost 50% of the header fields are entirely supported, which is represented in green, and that another about 40% are on average partially supported, which is represented in yellow. Partial support for browsers means that the browser does not react on the header field, for example, due to version information that is irrelevant for the browser or incomplete feature support. Most importantly, only a few header fields received no support, which is indicated in red. However, all of these were considered deprecated and thus intentionally ignored. Based on these results, we can confirm that browsers are in general secure and support recent security-related header fields. But how is the situation for generic HTTP libraries and classes? Let's have a look at them. Here we have a look at the HTTP header field support in libraries. The support for security-related header fields is very limited in HTTP client libraries compared to web browsers. In fact, most of the header fields are not supported, and most of the remaining header fields received only partial support. For libraries, that means that there exists a code stub that can detect the presence of a header field, but it contains no application logic. Only very rarely, some features are supported in these clients. Finally, we look at the HTTP header field support in commonly used Java classes. And it gets even worse. No header field is entirely supported, and in particular, the socket class does not support any header field at all. However, this is because it does not operate on the HTTP application layer. After seeing these findings, you may wonder whether any efforts have been made to allow HTTP client libraries and classes to benefit from header fields. This is a screenshot of a reported issue on GitHub in one of the most prevalent HTTP client libraries used in mobile apps, called OKHTTP. A developer deliberately asked for the implementation of the strict transport security header field and received support from many peers. However, it is still not yet implemented, and the library developers argue that the space requirements and the existing other facilities do not justify the implementation of such a feature. In consequence, they still leave their users vulnerable to attacks which could not happen in modern web browsers. So what did we observe when looking through these header fields? Product names or version schemes are ubiquitous, although developers should generally avoid them. Then we observed that unprotected HTTP communication is still very prevalent, although developers should use the secure HTTPS instead. And finally, we realized that the HTTP strict transport security feature is not widely used in the web communication of mobile apps, and that developers cannot leverage this feature easily because it is not well supported on mobile HTTP clients. But is there something we can do? We believe that the answer to this question is yes. And for that purpose, we would like to discuss two new header fields. The first header field X allowed interpretation declares whether it is safe to process the received data with interpreters for a specific computer language. I will now show three corresponding header field values that illustrate the use of such a feature in your application. The value any would not restrict any interpretation and the application would work as usual. The value none would prohibit any interpretation and effectively prevent further execution of code if the environment detects that such data ends up, for example, in a SQL query string. In the last example, the value SQL would allow the use of the received data in SQL query strings. Now let's continue with the second header field. The second header field declares whether it is safe to store the received data. I will now again show three corresponding header field values that illustrate the use of such a feature in your application. The value any would not restrict any storage options and the application would work as usual. The value encrypted would only allow the storage of encrypted data. Therefore, a developer would have to encrypt the received data in order to save it on disk or log it to a console. Finally, the value none would prevent a developer from storing a particular piece of data. However, the more comprehensive use of existing header fields and our proposals introduce open questions that have not yet been answered, such as which features can be adopted in generic HTTP clients. Another open question is, how can we ban advertisement-related header fields? And finally, are the proposed security headers useful in practice? We conclude with this picture that nicely summarizes the current state of HTTP security in mobile apps. Most apps use insecure or inappropriately configured communication channels and let everyone access their transmitted data. Even worse, server operators are exposing sensitive information in their HTTP headers, giving attackers tools to infiltrate their systems. And this concludes my presentation. Thank you very much for your attention.